Hi, and welcome back. So I'm happy to say that today we're going to really start getting into statistics proper. And the topic today is going to be sampling distributions. So what's the name of the game? We're going to be looking at the process of trying to study a population, finding out some facts about it by taking some sort of random sample of its population. And of course, because this is mathematics, we're going to need to abstract that just a little bit. And so for the purposes of our investigation, we'll define the term population to be really the result of some measurements, the potential results of the measurements. These are, this is a set of potential measurements, a set of numbers from which a sample will be drawn. A collection of observations. So such a thing is modeled typically after some type of random variable. So we think type of random variable, and by that I mean something described by, for example, a cumulative distribution function or a probability density function or something like that. So something which determines what kind of measurements and the distribution of those measurements. A random sample will be a finite collection of such measurements. So more precisely, this is a collection of independent and identically distributed random variables. But we're thinking about these as measurements from the population. By which really just mean that the original population is given by having some distribution, and these independent and identically distributed random variables, their distribution is according to the distribution that describes the population. Okay. Now, we take some random sample and we look at it and we examine that random sample. That random sample is some collection of numbers, and observations about it are going to be functions depending on that collection of random numbers. And that is kind of the basic I can't spell apparently. That's going to be the basic bread and butter thing that we look at, a statistic. Hopefully I can spell the word statistic for the purposes of this course. A statistic is going to be a function of these random variables. I guess I should have given them a name up here. In the random sample, this is given by some list of random variables x1 through xn, and this is a function of the random variables x1 through xn in our sample. So for example, maybe you're interested in trying to figure out the mean of a population. And so what do? You take a bunch of measurements and you examine the mean of your measurements. So that's an example, or I should say maybe the average of your measurements. So the sample mean is this particular function of the random variables. It's the sum of your random variables divided by n. So this, in other words, is a random variable which takes in measurements and returns back the average value of those measurements. Here's another useful random variable. The sample variance is defined to be the sum of your random variables minus the mean. Now, the mean is not a number here. We should be careful. This is a random variable, right? Squared, excuse me, divided by n minus 1. Okay. Notice n minus 1 and not n. This is just the definition of the sample variance. Okay. So again, it's useful to stress that these things are not numbers. They are not the values of these, of kind of the mean of the population or something like that. This is just a random variable, which is meant to kind of reflect that mean, for example. Okay, well, so from that point of view, we should ask the following question. Here's a very basic question. Suppose you're interested in, for example, the mean of a given population. How well does the sample mean reflect the mean? Okay, so what might we mean by that? So how well, this is an informal question, does X bar reflect the mean? Okay, so of course we can say a couple of things off the bat. We can talk about the expected value of the sample mean and the variance of the sample mean. We know how to do that kind of thing, so let's just briefly do it. So of course the expected value is the expected value of this sum. So the sum is from I equals 1 to n, but I guess I'm being a little lazy and not writing that. Of course, the 1 over n pulls out by linearity of expectation, and also by linearity of expectation, the sum pulls out. And you get the sum of these independent and identically distributed random variables. So when I say mu here, of course, I mean the mu which describes the entire population. So all of these things are identical random variables, and mu is that common mean to each of these random variables. And in particular, when we're looking at the expected value of xi, the expected value is mu. It's that same mu for each of them. So altogether, that's an n out of 2. Altogether, I have n of these things in the summation, and they're each mu. So of course, the expected value of the sample mean is the population mean. That's not a big surprise, obviously. What about the variance? Again, this is something that we've seen before. The variance of X bar. So the variance of a sum. This is just a warm up. You guys are just warming up here, right? The variance of a sum. Again, variance when you have excuse me, when you have a scalar like that 1 over n, it pulls out via the square. The variance has this kind of quadratic property. And now, if you have the variance of a sum, so remember, if these are independent, then it is linear. And just so we remember just very briefly why that is, it's just you're taking really the covariance of the sum with itself. And when you do that, then the covariance is linear in each factor. So you get some terms which look like, when you expand this over the two sums, kind of FOIL it out, you get some terms that look like covariance of xi, xj. Those are all 0 if I is not equal to j. And you get other terms that look like covariance of xi, xi. And those are the variance of xi with itself. So when you do that, you end up getting all those cross terms die, and the terms that remain are 1 over n, just the variance of xi. Excuse me, and you get a sum of those. So you get n of those. Each particular one of those variants is the kind of full variance of the population. That's because each of these is an identical, is a variable with this same distribution according to this population. We get 1 over n squared, and we get n times sigma squared, the population variance. And so you get 1 over n sigma squared. Okay. Okay, so the next question which we'd like to explore is, if we take a measurement from our population, if we take a sample, we'd like to know how close the sample mean reflects the population mean. So let's just take a concrete look at that to get a flavor. So let's suppose we have a population with variance sigma squared equals 64. Okay, so let's suppose we know the variance just for the sake of argument, but we don't know the mean, and we're going to try to estimate the mean. So we take a sample, let's say we have a sample size of n equals 32. Then we might ask, what's the probability, as a warm-up to this, that, that our sample mean is within 2 of the population mean? Yeah, so let's just ask, like, what's the probability that we are pretty close to the population mean? Okay, so fortunately, even though we really don't know about the distribution in our population, we haven't said anything about it, we don't know if it's normal or uniform or what, there is still a general purpose tool for applying to this kind of problem. For example, Chebyshev's inequality. So Chebyshev says that the probability of any given random variable being within k standard deviations of its mean is at least 1 minus 1 over k squared. Okay, so this is some general purpose tool that works for any random variable. And in our particular case, we're wondering what's the probability that this particular random variable, the sample mean, is within 2 units of its mean. So to apply Chebyshev, we need to write 2 in the form k times sigma x. So sigma x bar in this case, because we're looking at the standard deviation of the sample mean. So as we observed before, we know the variance of the sample mean. So the variance of the sample mean is going to be 1 over the sample size times the population variance. The population variance is 64 here, and n is 32. So this is, 64 over 32 is 2. And let's see, so that's sigma squared. So in other words, sigma would be the square root of 2. Okay, so this is k times root 2. So that tells us that the k is root 2 that we're interested in here. And so Chebyshev says that this is at least 1 minus 1 over root 2 squared, which is 1 minus a half, which is a half. So this isn't like super awesome accuracy here, but it's telling us that there is a 50-50 chance, there is at least a 50-50 chance that that the probability of x being that close to the of our sample mean being that close to the population mean, so there is, okay, let me say that again. The probability that our sample mean is at least within at most 2 units of the sample. The probability that our sample mean is within 2 units of the population mean is at least a half. Okay, so so in other words, the probability, let me just write it like this, that okay, well, so x is within 2 units of the sample mean, but I could squint and look at that a little bit differently. I could say, I could think of this as the probability that that the population mean is within 2 units of the sample mean, right? And so really what I could say as well is that the probability that x minus 2 is less than or equal to mu is less than or equal to just strictly less than, I guess, there, x bar plus 2 is at least a half. So in other words, we are at least 50% certain, let's read this, we are at least 50% certain that mu is between x bar minus 2 and x bar plus 2. Okay, so by making this measurement, we have some estimate on how sure we are that the mean is within those bounds. Okay, that's I guess that's pretty crappy though, right? I mean, 50%, right? We can do a little bit better if we had more information. So like, for example, like what if we knew that the population was normally distributed? Right, Chebyshev works for any kind of distribution, but if you have a normal distribution, then well, that's a lot more information. So just to move through this a little bit quickly, let's see what we could say. Okay, so of course X bar, as we observed, has mean the same as the population mean, and variance 2. And what that says is that X bar, because it's because X bar is this average of normal variables, it is also normally distributed. So this is normally distributed. So that's just because you add a bunch of normal variables together, you get a normal variable, you divide it by n, you get another normal variable. With that mean and variance, and that tells us that if you subtract off, if you subtract off the mean, I'm not sure where that came from, and you divide by the standard deviation, square root 2, that this thing is a normal random variable. So we're just assuming that this actually is normally distributed. So that is a normal random variable, standard normal random variable. Okay. And so now if I wanted to estimate the probability that, that the sample mean minus the actual mean is less than or equal to 2, well, that's the probability that let's just divide this out, that X bar minus mu over root 2 is less than or equal to 2 over root 2, which is root 2. That's the same probability there. And that's the probability that my standard normal random variable, that the absolute value of my random normal variable is less than or equal to root 2. Okay, so that's the probability that my normal random variable is between minus root 2 and root 2. And you know, you can look that kind of thing up in a chart. So this is like about minus 1.4 and 1.4. And so you look that up in a table in the back of, you know, your favorite statistics book. I might even know what that statistics book is, but you look it up in your favorite one, and you find that I think I found that this is roughly 84%. I got 0.83 something, 0.84, let's say. Okay. So in other words, if we knew that it was a standard variable, then we get that that the probability that that the mean is within 2 units of my observed value is approximately 84%. The nice thing about this is, unlike Chebyshev, where we just had a bound, this is supposed to be a, you know, this is actually an estimate, you know, just an estimate because I looked it up in the table. If you know, and I rounded everything off. But so this is really actually what the probability is, that the you know, that the population mean is going to fall between these two random variables. Okay, so that's just some examples of how we can use the sample mean to estimate stuff about the population, in this case, the mean.